Alright, with all of those rules I've proved, we're going to move on to a topic called continuity. And it starts with this. If the limit as x goes to a, f of x, equals f of a, then f is continuous at a. If f is continuous on B, comma, C, I'm making a closed interval for now, then f is continuous at every point in the interval. Visually, it's pretty easy. You're just looking for breaks and things like that in the graph. So, I grabbed this function from before. Let me pull it up just a little bit here. And I want to list the intervals where this is continuous. So, this graph here is continuous on, we'll say something like continuous on. And we'll list the x-axis. And we'll list the x-axis for which it happens. So if you look, let me look at the graph down here. If I go from 4, make this a little, from 4 to negative 3, you see that the graph along there is not broken until you get to negative 3. There is a point at negative 4 for which it is defined. At negative 3, there's a jump. So I would list this as negative 4, but I have a bracket over there to indicate that negative 4 is included up to 3, and I put a parenthesis. Now then, I'll use the union symbol because there's more intervals involved in the answer than just what I wrote. If we go then, starting from negative 3, if I go and I see that it's unbroken all the way, the graph is unbroken all the way until x gets to negative 1. So this part right here, you can see this, that it has a hole at the beginning and the end of that interval. So from negative 3 to negative 1, parentheses for both, it's continuous. For another union. Now we're looking from negative 1 to 1, which is this piece of the graph up here. There you can see that at negative 1, we include that, but we don't include positive 1. So I'll put negative 1, 1, comma, or parenthesis. Then the next piece that I have is this one right here, and that goes from negative 1 to 2, not including 1, but including 2. So I'll continue my union. We have 1 to 2. Actually, that 2 fooled me. Let me get rid of it. Because the fact that they highlighted, or that they put a dot here, kind of led me to believe that I should stop there, but I shouldn't. Actually, if you look, there's no break in the graph from here all the way until we get to 4. So from 1, not including 1, all the way to 4. So those are the intervals where it's continuous on. Now, I went through a lot of trouble proving a bunch of things before. The latest one was the limit as x goes to a, sine of x equals sine of a. I have the limit as x goes to a, x equals a. I have the limit as x goes to a of c. C is some constant. As the limit as x goes to a f of x times g of x equals the limit as x goes to a of f of x times the limit as x goes to a of g of x. And then I proved that the limit as x goes to a 1 over f of x equals 1 over the limit as x goes to a f of x. Of course, the assumption here is that the limit x goes to a of f of x does not equal 0. What else? We did roots too. The limit is as x goes to a, the nth root of x equals the nth root of a. Of course, this is subject to a bunch of domain rules, like if n is even, then a is greater than 0. If n is odd, a can be any number. What this does for us is the following. Let's take a polynomial. This looks something like b sub n x to the n plus b sub n minus 1 x to the n minus 1 plus an x sub 1 x plus b. If I take the limit as x goes to a of p of x, that's the limit as x goes to a of bn x to the n plus bn minus 1 x to the n minus 1 plus dot 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 plus b1x plus b. I should put b sub 0, just indicate it's the last coefficient. Well, I think I missed one of these here. Let me throw it over here. The limit as x goes to a f of x plus g of x equals the limit as x goes to a of f of x plus the limit as x goes to a g of x. So, first thing I'm going to do is that piece. This is going to equal the limit. I'm only going to do this one time. I'm not going to do this a bunch of times. X goes to a of b n x to the n plus the limit as x goes to a bn minus 1 x to the n minus 1 plus dot dot dot. I'll break it down here. Plus the limit as x goes to a b1x plus the limit as x goes to a b sub 0. That's using the addition rule that I just had. Next, I can use the product rule. So I can do this. Let me work with just this one for a minute. To use the product rule, I can write that as the limit as x goes to a b sub n as x goes to a x to the n. Well, this is bn is a constant. It's just a coefficient. So that equals b sub n. Now this limit, according to the product rule, I can do this. How many times? Well, n times. That's using, I don't know why I changed addition, but that's using the product rule that I developed earlier for a total of n times. But that just equals b sub n, a times a times a times a, n times, which equals b sub n, a to the n. Without further ado, I can do the same business on each of the other terms. So what happens in the end is that the limit as x goes to a, p of x equals b sub n, a to the n, plus b sub n minus 1, a to the n minus 1, plus plus b sub 1, a, plus b sub 0. Well, that's equal to p of a. Since I didn't specify the a, this means that polynomials are continuous on the interval negative infinity to infinity. Rational functions. Suppose you have a rational function. Let's call it q of x equals p of x over r of x be a rational function. So p of x and r of x are both polynomials. I know then that the limit as x goes to a, q of x equals the limit as x goes to a, p of x over the limit as x goes to a, r of x, assuming that this limit in the denominator is not equal to 0. We now know from what I just did that this equals p of a over r of a, which is exactly the same as q of a, assuming that a doesn't make the denominator 0. So, rational functions are continuous wherever they're defined. I went through all the other things. I'll just start now writing the rest of the things down. Trig functions are continuous wherever they are defined. The reason why is because I went through the effort of showing that the limit at x goes to a, sine of x equals sine of a, and it didn't matter, so sine function is continuous on all real numbers because its domain is a set of all real numbers. So you can get remember cosine of x can equal plus or minus the square root of 1 minus sine squared of x. Well, if I look at the limit as x goes to a of cosine of x, the plus or minus, it'll be plus. You think if this is a plus or minus 1, it's not going to be affected by any kind of a limiting process. And of course, assuming we're not dealing with anything that's going to be negative, and that's impossible since the biggest this piece can be is 1, so it's not going to be negative. But I did for roots also, you can slip the limit process to the inside of a root. The 1 is unaffected by this process, and then when it comes to sine, think of it as sine times sine. The limit as x goes to a of sine of x is sine of a. This sine squared of a. which equals cosine of A. So sine and cosine are continuous on negative infinity to infinity. And we know that, you know that based on the graph. You've never seen, there's no holes or breaks in the graphs of anything. And these, whenever I write these intervals, I'm talking about the x values. Next then, all the other trig functions are going to be some sort of a fraction involving sine or cosine or both. So that's why they're continuous wherever they're defined. Did I get the roots yet? Let's go back here. No, let's do that one. So anything like this, continuous on 0 to infinity if n is even, and it's continuous on negative infinity to infinity if n is odd. Please note, the limit as x goes to 0 of the nth root of x does not exist if n is even. The reason for that is because I can go from the left or right. Instead, I'm stuck with this. I must approach 0 from the right-hand side in order for me to use values of x for which the nth root is defined. That's why I write, if you look up here where I have the absolute value, not the absolute value, the bracket, it's because I cannot come in from the left side, so this makes it look like, and as it should, that the only numbers you're dealing with are 0 and those to the right of 0. Typically what will be done then is the types of questions you'll have will be like, where are certain functions continuous? So let me do an example. Over which intervals is, let's say, f of x equals x squared plus 3x minus 10 divided by, that was a 10, not a 16, so let me change that to a 10, over 2x squared plus 7x minus 15, over which intervals is f of x equal all that continuous. So what you need to do immediately is recognize that this is a rational function, so it's continuous wherever it is defined. So the only where it's not defined is where the denominator is equal to 0. So let me find those places. So I'll set 2x squared plus 7 minus 15 equal to 0. If I luck out, this will factor. And if it does factor, it's going to look something like this. It shouldn't be that hard to do the rest. Let's see, I need to have a 15 come out when you multiply the last part of it in the FOIL method. So the only way I can do that is a 1 and a 15 or a 3 and a 5. So let me see, 1 and a 15, if I put these in here, at some point I'll have 15x, and that'll make either 16x or 14x, which is not going to work for me. So let's get rid of those. And even if I swap them, put a 15 here and a 1 here, when I do this, I'll get a 2x mixed with a 15x. So the best I'm going to get there is either 17x or 13x of some sort, positive or negative, of course. So pretty quickly, I don't like the looks of 15. I'm going to go with 3 and 5 and see what happens. Start with 3 here and a 5 here. Let's take a look. when I do 2x times 5, that's a 10, and then 3x. Well, I can get a 7x out of that. If I make this positive, because that would give me positive 10x minus 3x. So from this, we get x equals 3 halves, x equals negative 5. Remember, those are the places where the denominator is 0, so I don't want them. So the answer to that question is negative infinity to negative 5 union negative 5 to 3 halves union 3 halves to infinity. So you can see I'm specifically plucking out the two x values that were not permitted to be had. At this one, as another example, determine where f of x equals the square root of 1 minus 1 over x is continuous. So remember, this is pretty much wherever it's going to be defined. You have a square root mixed with a rational function on the inside. So I'm basically just going to look for places where that's not defined. The first thing you notice is this. Since we're dealing with the square root, I have to have 1 minus 1 over x be greater than or equal to 0. There's a variety of ways of doing these things, and being tricky about it is probably not the best thing to do. The last thing you want to do is multiply by x because you don't know if x is positive or negative. So you wouldn't know whether to switch the inequality sign. Better to do this. Rewrite the 1 as x over x so that you can combine the fractions. So when I do that, I have x minus 1 over x. That's greater than or equal to 0. So the only places where it's equal to 0 happens when x equals 1, and it is undefined when x equals 0. So obviously x cannot equal 0. What people typically do is draw a number line, and on this number line indicate the important values. 0 is one of them, and so is 1. I like to do something a little special with 0, and I do this. I didn't mean to take out the whole line, but that's the way this thing works. So put it back. I want to put a hole in that to indicate to me that you cannot have that value for x. Now the task is to try to determine where this expression is positive versus where it's negative. And the way you do that is you take values of numbers in each of these intervals, negative infinity to 0, 0 to 1, and then 1 to infinity. And then plug them into this thing to see if you get a positive or negative. For example, if I pick, as I pick like negative 1, they call this a test point. Let's see what happens when I plug negative 1 in for x. So I'll have negative 1 minus 1 divided by negative 1. That's equal to a positive 2. What I'll do here is put a plus to indicate that it's positive on that interval. Same thing. Now, this is a little more complicated. Here, I'll test, say, positive 1/2, sorry. So let's plug it in there. So I'll have 1/2 minus 1 divided by 1/2. I really don't care about actually evaluating it because I can tell that I'm going to get 1/2 minus 1 is going to be a negative number in the numerator divided by a positive number in the denominator, forces this section here to be negative. Finally, pick some number greater than 1, so I'll try test 2. Let me plug it in. 2 minus 1 over 2. It's easy to see that you get positive 1/2. So, what's the answer to this one? I only want the positive symbols, because that's where the whole thing is defined, and of course leave out 0. So I'll have negative infinity to 0. I won't include 0. Union, but I will include 1 because it is allowed, x is allowed to include 0. Union, but I will include 1 because it is allowed, x is allowed to equal 1. So there we go there. I had one more that I wanted to try, and it involves a trig function. Let's do example. Determine where f of x equals secant of 1 over 1 minus x is continuous. Now, in situations like that, it's sometimes, to write the interval would be extremely messy in some cases. Instead, we notice that secant of x is continuous, or, well, yeah, it's continuous, is continuous wherever it's defined. So secant of x is continuous for, I think it's easier to do this, x not equal to odd multiples of pi over 2. Remember, secant is 1 over cosine, and cosine is 0 at odd multiples of pi over 2. And if you want a cool symbol to just throw into your arsenal, you can use this weird-looking z, which stands for the set of integers. So if we apply this statement here, then I know that 1 over 1 minus x is not supposed to equal 2k plus 1 times pi over 2. Now, the way you would solve something, it's weird to be solving a not equality, but if I flip both sides, I get this. 1 minus x is not equal to 2 over 2k plus 1 times pi. Subtract 1. Negative x cannot equal 2 over 2k plus 1 pi minus 1. And then I'll multiply both sides by negative 1. And this is better, and don't forget to tell me that k is a member of the integers. So k could be any integer. Now, these here are all the odd multiples of pi over 2, but upside down. Now, if we go back, I got to be a little careful here, because there is one other place here. X cannot equal 1, because that would make the denominator 0. So what I'll do is, actually for my answer, I'll put this. X cannot equal 1 minus 2 over 2k plus 1 pi. K is in z. And x cannot equal 1. So I'll use this as my whole answer. I'm sure there's cooler ways of doing it than that, but that gets all the information that I need. That would be an extremely difficult thing to describe using intervals. So